Welcome to Space Theory, the channel where we explore the mysteries of the universe and uncover the wonders of space. Join us for astronomy, astrophysics, and space exploration. So, buckle up and get ready for a cosmic adventure. Introduction. Imagine waking up one day to find out that everything you know about the universe is a lie. What if the stars, the planets, and even time itself are mere illusions? This mind-bending scenario might sound like science fiction, but recent claims by some physicists suggest that the universe as we know it might not exist at all. This radical idea challenges our very understanding of reality, sparking debates that could redefine the boundaries of science and philosophy. But how could this be possible? Let's dive into the depths of this extraordinary hypothesis and uncover the astonishing arguments behind it. Basics of quantum mechanics. Quantum mechanics is a branch of physics that deals with the behavior of particles on the smallest scales. It emerged in the early 20th century as scientists began to uncover phenomena that classical physics could not explain. At its core, quantum mechanics challenges our traditional notions of reality, determinism, and locality. Particles such as electrons and photons do not behave like tiny billiard balls, but rather exhibit both particle and wave-like properties. This duality is central to understanding the quantum world. Superposition and Schrödinger's cat. One of the most intriguing aspects of quantum mechanics is the principle of superposition. According to this principle, a quantum system can exist in multiple states simultaneously until it is measured or observed. This idea was famously illustrated by physicist Erwin Schrödinger in 1935 through a thought experiment known as Schrödinger's cat. In this scenario, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. Quantum mechanics suggests that until the box is opened and the system is observed, the cat exists in a superposition of being both alive and dead. Implications for reality. The concept of superposition has profound implications for our understanding of reality. If particles can exist in multiple states until observed, does this mean that reality itself is indeterminate and only solidifies upon observation? This question has led to intense debates among physicists and philosophers. Some interpretations, such as the Copenhagen interpretation, suggest that the act of measurement collapses the wave function, determining the state of the system. Others, like the many worlds interpretation, propose that all possible outcomes of a quantum measurement actually occur, each in a separate parallel universe. These interpretations challenge our traditional notions of a singular objective reality. The observer effect. The observer effect is a phenomenon in quantum mechanics where the act of observing or measuring a quantum system affects its state. This concept is closely related to the principle of superposition and the collapse of the wave function. When a quantum system is not being observed, it exists in a superposition of multiple states. However, when a measurement is made, the wave function collapses and the system assumes a definite state. This suggests that the very act of observation plays a crucial role in determining the properties of a quantum system. Historical experiments. One of the most famous experiments that demonstrate the observer effect is the double-slit experiment. In this experiment, particles such as electrons or photons are fired at a barrier with two slits. When both slits are open and no observation is made, the particles exhibit wave-like behavior, creating an interference pattern on a screen behind the barrier. However, when detectors are placed at the slits to observe which slit each particle passes through, the interference pattern disappears, and the particles behave like classical particles, forming two distinct bands on the screen. This experiment highlights the role of observation in determining the behavior of quantum systems. Philosophical implications. The observer effect raises profound philosophical questions about the nature of reality and the role of consciousness. If observation affects the state of a quantum system, does this mean that reality is inherently subjective and dependent on the observer? Some interpretations of quantum mechanics, such as the participatory anthropic principle, suggest that consciousness plays a fundamental role in shaping reality. This idea challenges the traditional view of an objective observer, independent universe, and suggests that the act of observation and the existence of conscious observers are integral to the nature of reality itself. The simulation hypothesis. The simulation hypothesis is the idea that our reality could be an artificial simulation created by an advanced civilization. This concept gained widespread attention after philosopher Nick Bostrom published a paper in 2003, arguing that one of three propositions must be true. 1. Advanced civilizations do not reach a stage where they can create simulations of reality. 2. Advanced civilizations have no interest in creating such simulations. Or 3. We are almost certainly living in a computer simulation. Bostrom's argument is based on probabilistic reasoning and the assumption that if it is possible to create many simulations, it is more likely that we are in one of the many simulations, rather than in the one base reality. Nick Bostrom's argument. Bostrom's argument for the simulation hypothesis is built on the premise that advanced civilizations will eventually possess the computational power to create highly detailed simulations of reality. If such simulations are possible, it is likely that many such simulations will be created. Therefore, the probability that we are living in the one base reality, as opposed to one of the many simulations, is extremely low. Bostrom's argument hinges on the assumption that future civilizations will be interested in creating simulations and that they will have the technological capability to do so. Technological feasibility. Advancements in technology, particularly in the fields of computing and artificial intelligence, lend some plausibility to the simulation hypothesis. Virtual reality and augmented reality technologies are becoming increasingly sophisticated, and computer simulations are already used in various scientific and engineering applications. If technological progress continues at its current pace, it is conceivable that future civilizations could create simulations indistinguishable from reality. Additionally, developments in quantum computing could provide the computational power necessary to simulate complex systems, further supporting the feasibility of creating simulated realities. Counterarguments and criticisms. Despite its intriguing nature, the simulation hypothesis faces several criticisms. Some argue that the computational resources required to simulate an entire universe would be prohibitively large, even for an advanced civilization. Others question the assumption that future civilizations would be interested in creating simulations, suggesting that ethical considerations or other priorities might take precedence. Additionally, some critics point out that the hypothesis is unfalsifiable, meaning it cannot be proven or disproven, and therefore falls outside the realm of scientific inquiry. Despite these criticisms, the simulation hypothesis remains a compelling and thought-provoking idea that challenges our understanding of reality. The holographic principle. The holographic principle is a theoretical concept in physics that suggests that all the information contained within a three-dimensional volume can be encoded on a two-dimensional boundary of that volume. This idea is analogous to a hologram, where a three-dimensional image is encoded on a two-dimensional surface. The holographic principle was first proposed in the context of black hole physics by physicists Gerard Hooft and Leonard Susskind in the 1990s. It has since been extended to more general settings in theoretical physics, including string theory and cosmology. Historical context and development. The holographic principle emerged from attempts to reconcile the apparent contradictions between general relativity and quantum mechanics in the context of black holes. According to the principles of general relativity, information about matter falling into a black hole appears to be lost to the outside universe, leading to the so-called information paradox. However, the laws of quantum mechanics suggest that information cannot be destroyed. The holographic principle provides a potential resolution to this paradox by suggesting that all the information about the matter falling into a black hole is encoded on its event horizon, a two-dimensional surface, rather than being lost within the black hole. Scientific evidence and theoretical support. The holographic principle has received significant theoretical support from developments in string theory and the Adsikoft correspondence, a conjecture proposed by physicist Juan Maldacena in 1997. According to the Adsef correspondence, certain theories of gravity in a higher dimensional space, anti-de Sitter space, are equivalent to quantum field theories on the lower dimensional boundary of that space. This correspondence provides a concrete realization of the holographic principle and has led to numerous insights in theoretical physics. Additionally, studies of the cosmic microwave background radiation and the large-scale structure of the universe have provided indirect evidence that supports the holographic principle. Impact on our understanding. If the holographic principle is correct, it has profound implications for our understanding of space, time, and the nature of reality. It suggests that our three-dimensional universe may be a projection of information encoded on a two-dimensional boundary, challenging our conventional notions of dimensionality and locality. This idea also has implications for the nature of black holes, the structure of space-time, and the unification of general relativity and quantum mechanics. The holographic principle represents a significant shift in our understanding of the universe and continues to be a topic of active research and debate in theoretical physics. Conclusion. The idea that the universe might not exist is both fascinating and unsettling. It pushes the boundaries of science, philosophy, and our perception of reality. While these theories are still speculative and hotly debated, they remind us of the profound mysteries that remain unsolved. As we continue to explore the cosmos and delve deeper into the quantum realm, we may uncover truths that are stranger than fiction. Until then, the question remains, does the universe exist, or are we living in a grand illusion? Only time, and perhaps a bit of imagination, will tell.